UV visible spectroscopy, or it is also called electronic spectroscopy. So in this lecture we will learn about UV visible spectroscopy. So earlier I said that spectroscopy is the study of interaction of electromagnetic radiation with matter. Now UV visible spectroscopy is for molecules, so it is molecular spectroscopy. Now, what interaction does this UV visible radiation do with molecules? For that, let us recollect the atomic spectroscopy. In atomic spectroscopy, electronic transitions in atoms are taking place between the atomic orbitals in an atom. And you are well familiar with the atomic spectrum of hydrogen, which consists of several series of lines which are called the Lehman, Balmer, Paschen, Bracken and Fund series, and these are characterized by lines and they are also called the line spectrum. But now we are concerned with the spectroscopy in molecules. So when atoms combine to form molecule, there are no longer atomic orbitals present in the molecules. The atomic orbitals combine to form molecular orbitals. So the electronic energy levels present in a molecule are the molecular orbitals, and in order to undergo transition between these electronic energy levels or the molecular energy levels in a molecule, energy is needed from the UV visible region of the electromagnetic spectrum. That is, only if the light from the UV visible region is used, the transitions among the molecular orbitals or the electronic energy levels in the molecule will take place. So for that, we will just recollect how a molecule is formed by combination of two atoms. So for that, recollect the formation of hydrogen molecule, and hydrogen molecule is formed by combination of two hydrogen atoms. And these are two isolated hydrogen atoms, and these are the atomic orbitals of hydrogen. This is the 1s orbital of one hydrogen atom. This is the 1s orbital of another hydrogen atom. So when they combine to form molecule H2, these atomic orbitals overlap, and this overlapping leads to formation of molecular orbitals. And the overlap can be by addition of the two atomic orbitals, and if the two atomic orbitals are added, we are getting a molecular orbital where the electron density is more in between the two nucleus, and this leads to formation of the bonding molecular orbital sigma 1s. And when the two atomic orbitals subtract, you get a molecular orbital where the electron density is 0 in between the two nucleus, that is, there is a node, and this is called the anti-bonding molecular orbital sigma star 1s. So this is sigma bond, and there are two types of molecular orbitals when a sigma bond is formed, which is sigma bonding molecular orbital and sigma star anti-bonding molecular orbital. This is the overlap of two 1s orbitals. Overlap of two p orbitals is also possible when the p orbitals lie along the internuclear axis. So this is the internuclear axis. The axis which is formed by joining the two nucleus is the internuclear axis. So when the two p orbitals lie along the internuclear axis, they overlap axially and form sigma 2p molecular orbital, bonding molecular orbital, and sigma star 2p anti-bonding molecular orbital. If the two p orbitals are perpendicular to the internuclear axis, they overlap sidewise and they form two molecular orbitals, bonding pi molecular orbital and anti-bonding pi star molecular orbitals. So if a sigma bond is formed, then the molecular orbitals formed are sigma and sigma star. And if the molecule has pi bonds, then the molecular orbitals are pi and pi star. If a molecule contains molecular orbital with lone pairs which are not involved in bonding, they form the non-bonding molecular orbital, represented by N. So in a molecule, the atomic orbitals combine to form molecular orbitals, and this can be sigma, sigma star, pi, pi star, and molecular orbitals which contain lone pairs are called non-bonding molecular orbitals. Now transitions are taking place between these molecular orbitals. So the molecular energy levels, the level and the symbol can be represented in increasing order of energy. Lowest energy is for the bonding sigma, represented by sigma. Highest energy is for anti-bonding sigma, represented by sigma star. Then bonding pi has energy more than the bonding sigma. It is represented as pi. Anti-bonding pi has energy which is lower than the anti-bonding sigma. It is represented as pi star. The non-bonding molecular orbital has energy in between this. So this is the increasing order of energies of the energy levels in a molecule. Sigma, pi, n, pi star and sigma star. Now in order to carry out the UV visible spectroscopy, we are using the radiation from the UV visible region. So the wavelength range used are from 100 to 200 nanometers. It is called the far UV or vacuum UV region. From 200 to 400 nanometers, it is called the near UV region. Both these together form the UV region. From 400 to 800 nanometers is the visible region. Now for carrying out the UV visible spectroscopy, the vacuum UV region is not used. So the electromagnetic radiation used in UV visible spectroscopy lies in 200 to 800 nanometers, which is covering from UV to the visible region. Now how is the spectral data presented? So let a sample be exposed to radiation in the UV visible region and I0 be the intensity of the incident radiation. So when light falls on a homogeneous medium, a portion is absorbed, IA, and the remainder is transmitted, which can be represented as IT. So I0 is the intensity of the incident light, IA is the intensity of the absorbed light, and IT is the intensity of the transmitted light. So I0 will be equal to IT plus IA. Now the term IT by I0, that is the fraction transmitted. IT is the intensity of the transmitted light, I0 is the intensity of the incident light. So IT by I0 will be the fraction of radiation that is transmitted. And IT by I0 is called the transmittance. Represented by capital T. And the term log I0 by IT is called the absorbance, represented by capital A. It is also called optical density, represented by capital D. Now it is found that this absorbance is proportional to the concentration of the solution taken in this. So concentration C. And it is also proportional to the path length. That is the length travelled by the light, which is nothing but the length of this container, and this container is what is called a cuvette. And usually this is 1 centimeter. So we can write A is equal to a proportionality constant epsilon into C into T, where T is the path length. And the proportionality constant epsilon is called the absorptivity. Now the instrument used for measuring UV visible spectroscopy is called a UV visible spectrometer. And the absorption spectrum is obtained by plotting absorbance along the y-axis and wavelength along the x-axis. And wherever absorption is taking place, you are getting a peak. And this is the maxima of the peak, and the wavelength corresponding to the maxima is called the lambda max. So the wavelength corresponding to the maximum absorbance is called the lambda max. This wavelength of maximum absorption, lambda max, is reported in chemical literature. The instrumentation for this is the UV visible spectrophotometer. A modern spectrometer consists of a radiation source consisting of a tungsten filament for producing visible light and a deuterium discharge tube for producing ultraviolet radiation. These radiations are passed through a monochromator, which automatically select the required wavelength, and the monochromatic beam is split into two parallel beams, one of which passes through a transparent cell containing the sample. This is the cell containing the sample. I said the name of the cell is cuvette, and this beam is called the sample beam. The second beam is directed towards another cell containing only the solvent which is used for dissolving the sample. That is, this is the cell without the sample, and this is called the reference beam. And the two beams are electronically compared by a detector. Detector is usually a photodetector, and the intensities of the two beams are compared, and a plot of absorbance versus wavelength is automatically recorded over the desired range by the data processor. Now the solvents used for this must be very high grade of purity, and it must be free from substances that absorb in UV region, and it should be sufficiently transparent over the desired range of wavelength. That is, it should not absorb in the desired range of wavelength being measured. Example, 95% of ethanol is transparent up to 205 nanometers. Cyclohexane is transparent up to 195 nanometers. The other solvents used can be methanol, water, hexane. Now the cells used for taking the sample during the measurements can be made of glass or quartz. But for measurements in 200 to 400 nanometer region, quartz cells are essential. This can also be used for measurements beyond 400 nanometers. But if we want to do measurements only in the visible region like 400 to 800 nanometers, then we can use less expensive glass cells. A UV spectrum is obtained by plotting a curve of wavelength lambda along the x-axis against the absorption coefficient or the absorbance A or the optical density along the y-axis. A UV absorption spectrum of 2,5-dimethyl-2,4-hexadiene is shown here. The figure shows a broad band in the region 210 to 260 nanometers with a maxima at 241.5 nanometers. It is this wavelength or lambda max which is reported in chemical literature.